Hello everyone! In today's video what we're going to be discussing are some multiple choice questions. We're going to be going through OCR's Breadth in Physics paper from June 2016. As always, probably the best way to go about these questions would be to pause this video, attempt the question yourselves, and then check with my solution. Okay, well, let's have a look at question number 1. First off, the watt is the SI unit of power. That is actually one of my sort of favorite puns. What is the unit of power? Now that I've gotten this out of the way, let's have a look through the actual question, which is the correct definition for the watt. So a watt is the rate of work done, the work done per second, joule per second, or joule per unit time. Well, power is essentially energy divided by time. However, we're defining the watt. Sometimes you can indicate units with these brackets on the side. So if you're defining a unit, you need to define it in terms of other units. So a joule per second, because in all of those cases, a joule per second, both the joule and the second are units. So because of this, the correct answer is C. Moving on to question number 2. A crane is used to lift a load directly from point X to point Y. What is the work done against the weight? Now, this question actually takes a property of gravitational forces. They are known as conservative forces. So they're conservative forces. Now, that simply means that a conservative force, the work done by a conservative force is independent of the path. So that means that whatever path we take between X and Y, we can go along here, we can do that, we can move on along a different path, but as long as we go sort of from point X and we finish at point Y, the work done, and let me write that in a different color, the work done is always going to be equal to the force multiplied by the distance in the line at which that force acts. So in this case, the force which we are sort of working against is the weight, and the vertical distance along this line over here is just Q. So the correct answer is B. Work done is W multiplied by Q. So let me just write that. So that's B. Just a note, for example, if we're asked to determine the work done between, let's say, X and Z, sort of along this this path over here, and if there was a different force acting along here, then the work done would be FR, because R is the distance between them. So hopefully that makes sense. Let's move on to the next question. Okay folks, moving on to question number 3. A student views the display of a laptop screen for a polarizing filter. The intensity of the light changes once the filter is rotated. Which property of light is demonstrated in this experiment? Okay, so it has a wavelength of about 5 times 10 to the power of -7. Well, we're not really sure where they got that number from, so I'm going to go with no. It travels at the speed of light. This is definitely not the property that is being demonstrated in this experiment. It is a transverse wave. Well, it's being polarized, and only transverse waves can be polarized. So it's got to be C, and it's definitely not that it's a longitudinal wave, because a longitudinal wave cannot be polarized. So I'm just going to write over here that just for completeness, that only transverse waves can be polarized. So that's the property that's being demonstrated in this case. So the correct answer is C. Question number 4. Electrons traveling through a thin film of carbon are diffracted. Which statement is correct? The electrons behave like A. Photons. Well, that's obviously not correct. The electrons do not behave like photons and they're not deflected by the carbon atoms. B, photons and change direction as their speed changes. Well, this is essentially refraction, but we know that that's not true, so they don't refract. C, they behave like waves and are refracted by holes in the carbon film. Once again, well, they do behave like waves, but they're not refracted. What we're looking for is diffraction, and waves of wavelengths similar to a spacing between the carbon atoms. This is true because diffraction occurs. So I'm just going to write over here the diffraction. Oh, what happened here? Let's try again. So diffraction occurs, and that can only appear when the wavelength is of similar order to the spacings in the diffraction grid. So in this case, the atomic spacing between the carbon atoms is actually, it's got to be similar to the wavelength. So that means that diffraction will occur. By the wavelength, of course, I mean the de Broglie wavelength. If you're a little bit unsure about how particles can have wavelengths, please browse through the channel and you're going to find an early video that I made about particle wavelengths. But anyways, the correct answer in this case is D. Right, question number 5. In which region of the EM spectrum is radiation of wavelength 50 micrometers? Well, 50 micrometers, remember micro stands for 10 to the power of -6, so it is going to be 50 times 10 to the power of -6, which is about 5.0 times 10 to the power of -5 meters. Now this is not visible because visible is somewhere of the order of 10 to the power of -7, which is a few hundred nanometers. Infrared, yes, it definitely could be infrared because this is just a little bit bigger, and that's the next part of the spectrum. So let's just read through the next ones just in case. Now microwaves, these are of the order of a few centimeters, and this is considerably smaller, so that's not going to be that. And radio waves are quite big, so they're of the order of meters, so it's not that. So the correct answer has got to be B, infrared. Right, moving on to question number 6. The graph shows the resultant force on a football as it's being kicked. So you could put like a force sensor on a ball, and then you can plot that on a computer. Which of the following graphs relating to this kick would have had the same shape as the graph above? Acceleration of the ball against time. Well, as soon as we read A, we know that this has got to be correct. The reason for that is because the force is equal to mass times acceleration. So rather than force, just up here we could have equally have written ma. So just multiplying out by a constant, we're going to remain we're going to have exactly the same shape because m is just a constant. So the correct answer is A. Right, question 7. We've got a block of wood is at rest on a ramp, so that means all the forces are going to be balanced. The weight of the block is W and the frictional force on the block is F. A triangle of the forces can be used to determine the magnitude and direction of the normal contact force N, which is the correct diagram for this triangle. Okay, well now the secret to this question would be to actually draw the normal force on your diagram, and remember the normal force is always perpendicular to the surface. So normal actually means perpendicular, and let's just draw the normal force. So it's a vector which is sort of pushing upwards along here. Well, let's see which of those vector triangles keeps all of those forces in the correct orientation and the correct direction as well. So for A, W is pointing straight downwards, which is true, so W is pointing in the same direction as here. F is pointing upwards and to the right, which is fine, just as in our diagram here. However, you can see that the normal force is pointing downwards, where our normal force is pointing upwards, so it can't be A. Let's move on to B. We have exactly the same triangle, however the direction of the normal force is pointing upwards, so this has got to be correct. So the correct answer in this case is B. Question 8. The top end of two springs, S1 and S2, are attached to a rod. The mass is hung from the bottom end of S1, and so this one over here that has an extension X and has got an elastic potential energy E. Okay, the same mass is hung from the bottom of another spring called S2. The extension of S2 is X over 3, so 3 times is less of an extension. We can see that over here in the diagram. What is the elastic potential energy in the spring S2? Okay, well, just to make life a little bit simpler, let's call that E2. Let's write what we know. We know that the potential energy E, well, this is equal to half multiplied by the force multiplied by the extension. In this case, the force is the same because it's just the force due to the weight that is going to be the same for both of these objects. So because it's the same mass, this spring is going to have a force F pulling it down, and this spring over here is going to have exactly the same force F pulling it down as well. Now E2 is going to be a half multiplied by the force multiplied by X over 3, because the two extensions are different. The one on the left has an extension X, the one on the right has an extension X over 3. Well, let's see whether we can just find an expression for F. So what I'm going to do is I'm going to look at the first equation. I'm just going to say that the force is, just rearranging for the force, that's going to equal to 2E over X, like so. And what I'm going to do then is I'm just going to take that expression and plug it in this equation over here. So I'm going to get that my elastic potential energy of spring 2, call that E2, is going to equal to a half multiplied. Now rather than F, what I'm going to write is 2E over X multiplied by X over 3. And now we can do quite a lot of cancellation. So those 2's, they're going to go. So be gone 2's. Additionally, the X can be cancelled out. And before we know it, we're actually left with just one expression, which is E over 3. So the correct answer is B, E over 3. Okay, question number 9. A 9-volt battery is connected to two resistors as shown. Terminals X and Y connected to another circuit that draws a current of 1 milliamp over here. The current from the battery is 3 milliamps. So we have all the currents in the circuit. What is the power supply to the circuit connected between X and Y? Okay, well, the first thing to realize is that the power is going to be VI. We are given the current that goes between those 2 points when you connect something across it, and that's equal to 1 milliamp. What we need to find out is the voltage across the 3000 ohm resistor. As soon as we find that, we're in business. Well, the first thing that springs to mind is that we can really easily find the voltage across this resistor over here, because just V is equal to IR. Now the current going through this resistor, that's just 3 milliamps, as it says over here, so that's 3 times 10 to the power of minus 3, and the resistance is 1000 ohms, so times 1000. Those two are just going to cancel out, which leaves us with 3 volts. So we have 3 volts across here. Well, that means that if our total is 9 volts, we have 6 volts remaining for this one. Okay, well, if we have 6 volts remaining for the 3000 ohm resistor, we've actually essentially solved our problem, because now we know that our voltage across X and Y is also going to be 6 volts. And the reason for that is because the points X and Y are in parallel. They're across that they're across that branch. So the voltage between X and Y will also be 6 volts as with any parallel branch. So that means that the power between X and Y is just going to be 6 multiplied by 10 to the power minus 3 watts, which is a 6 milliwatts. Question 10, the halfway point. We have a trolley of mass m collides head-on with a trolley L. So there's a head-on collision between this guy over here and this guy over here. The mass of the trolley M is greater than the mass of the trolley L. The trolleys join together after the collision. Which statement is correct? The momentum of each trolley is conserved. Well, this is not correct. The reason for that is that only total momentum is conserved. So total momentum is conserved. So the individual momentum, I'm afraid, is not only the total momentum in a system. Trolley M experiences a greater force than trolley L during the collision. That's also not correct. The reason for that is because of Newton's third law. So each body is going to experience an equal force acting on it, and the two forces are going to be in opposite direction. C, the total force acting on the two trolling systems during the collision is 0. Let's see what that means. So that means that well, there's going to be two forces. Once those two guys collide, M is going to experience a force. Let's call it F, acting this way, and this one will also experience the same force F, acting the opposite way. So that statement has got to be true, because the total force acting on the two trolley system during the collision is 0. Just to be sure, let's just read through question for part D. Kinetic energy is conserved. Now that's only true for an elastic collision, and there's no that this is not an elastic collision, and there's no mention that this is an elastic collision as well. In fact, we know that it's not. So the correct answer has got to be C. Question 11. Two batteries are connected in a circuit with a lamp as shown. The batteries have an EMF 5 volts and 3 volts. Which row is correct? Now the first thing we notice is that the batteries are connected the other way around, so they're not going to add their EMFs, but in fact they're going to take them away. We know that because a minus is connected to a minus rather than a plus. So in this case the resultant EMF is going to look like this. So this is going to be our equivalent EMF of 2 volts, and essentially it's this circuit over here that I'm redrawing on the side with points X and Y across here. Which row is correct? So what is the direction of conventional current? Remember, conventional current is always from positive to negative. So the positive side is the slightly bigger side on the symbol for a cell. So in this case, this is our direction for conventional current, which is anti-clockwise. And if it's anti-clockwise, it's either going to be C or D. Points X and Y, well, those 2 points are part of a series circuit, so they're going to have exactly the same current going through them. There's no sort of loops or junctions for the current to go through. So the answer has got to be D, anti-clockwise. The magnitude of the current is the same at X and Y. Question number 12. The diagram shows conventional currents entering and leaving a junction in an electric circuit. Which statement is always true? Well, this question is a statement of Kirchhoff's first law. Now, Kirchhoff's first law says that the sum of the currents going in is equal to the sum of the currents going out of a junction. So in this case we can see that I1 and I3 are entering the junction. So I1 plus I3, these are our currents entering the junction. In fact, I'm just going to write over here that those over here are our currents entering the junction. and those are going to equal the current exiting the junction, which are I2 plus I4. Which of the following statements is true? Well, A, I1 plus I2, they're not going to have the same sign. That's not going to be true. So I1 plus I2 is not equal to I3 plus I4. It's not true. B, I1 minus I2 plus I3 minus I4 is equal to 0. Well, let's just rearrange this so that this, what we know is the true expression, equals 0. Well, as we know, these are the currents sort of exiting, by the way, so let me just write that. Okay, well, now let's get started with the rearranging. So I1 plus I3 minus I2 minus I4, this is going to equal to 0. And upon closer inspection, you can see that this is actually equivalent to B, because we can just rewrite this as I1 minus I2 plus I3 minus I4 is equal to 0. This simply stems from the fact that the sum of the currents entering a junction is equal to the sum of the currents exiting a junction. So in this case, our correct answer is B. Right, moving on to question number 13. A student determines the resistance R of a filament lamp by measuring the potential difference V across it and the current I in it. The values recorded by the students are the following. We've got the values for V and I with their absolute uncertainties. What is the percentage uncertainty in the value of R? Okay, well, the formula for R is that R is equal to V over I. Now in this case, we are dividing quantities. So if we divide quantities, what we need to do is add the percentage uncertainties. So we need to find the percentage uncertainty in V, we need to find the percentage uncertainty in I, and we need to add them. So remember, your percentage uncertainty in general is equal to plus or minus your absolute uncertainty divided by your value times 100. So we need to find the percentage uncertainty in V and the percentage uncertainty in I, then add them together. So our percentage uncertainty in R is equal to the percentage uncertainty in I plus the percentage uncertainty in V. Okay, well, let's find out the percentage uncertainty in I is just 1 milliamp over 40 milliamps times 100 plus the percentage uncertainty in V, which is going to be 0.2 over 5.00 times 100. And if we put that into a scientific calculator, what we're going to get is 6.5%. So correct answer is C. So question 14, a golf ball is dropped from a rest onto a hard floor. Okay, well, let's draw this. So here's our ball over here, and we drop that downwards onto a hard floor, and let's say that the hard floor is here. Okay, so then the ball starts bouncing from the time of release, at which point does the ball reach its maximum height after the first bounce? Okay, well, let's figure this out. So the ball drops down initially, and at point A the speed is 0. So this is essentially the speed of impact. So at point A the ball has 0 velocity. Now after that, the ball reaches maximum velocity again, sometime sort of straight after the bounce. So let's say that this is point B, probably a little bit lower, but we'll just keep it there for illustration purposes. So at point B we have the maximum velocity, and this is sort of straight after the ball sort of bounces back, and then it starts decelerating. Now as it bounces back, it's going to reach maximum height straight after that. So this is going to be point C, and we can see that at point C the speed is 0 again. So the speed is 0 at max height, v is equal to 0. Additionally, it's also 0 when it hits the ground, but for our purposes, at which point does the ball reach its maximum height after the first bounce, this is going to be point C. Almost there, folks. Question number 15. An electron gun is used to accelerate electrons from a rest through a voltage V. The electrons emerge with a speed u. Even before I carry on with the question, we can just write the main equation for this, and that is that EV is equal to a half times the mass times the speed squared. Now in this case, the speed is given to be u squared. Okay, so the voltage of the gun is half to v over 2. At what speed do the electrons emerge compared to the original speed? So what we can do is just rearrange for the first speed u. So we know that u is going to be equal to the square root of 2ev divided by the mass. So this is just rearranging for u. Okay, well, let's see what happens if we were to just halve the voltage. So I'm just going to do that on the side over here, just with a different color pen. And I'm going to use the same equation. I'm going to say that EV is equal to a half m. Rather than u this time, I'm going to call the speed v squared. And because I'm halving the voltage, I'm going to add a factor of v over 2. Okay, well, let's do exactly the same. I'm going to rearrange for v squared. Now, for v, in this case, this is going to be the square root of 2ev. Rather than just voltage, though, this is going to be the voltage over 2. So just fit it in over here. I'm just going to write times a factor of a half divided by the mass. Well, hang on a minute. These are almost the same expressions, aren't they? So this expression, 2ev over m, is exactly the same as this one over here. This is essentially u. So what I can do is just use the power of the properties of square roots. So I can just say that this is equal to the square root of 2ev over m times the square root of 1 over 2. And rather than 2ev over m, what I'm going to do is write u. So this is going to equal to u times the square root of 1/2. The square root of 1 is just, well, it's just 1, so this is just equal to u over the square root of 2. So in this case, the correct answer is C. Now, of course, you can definitely do this just a lot quicker just using proportionality. And you can think that in this expression, the speed is directly proportional to the square root of the voltage. So if you were to decrease the voltage by 1/2, because u is proportional to the square root of the voltage, you will decrease by a factor of the square root of 1 over 2. That's a different way of getting to the answer C, but I just wanted to show you the proper mathematical full derivation. Number 16. We have photons of energy 4.8 times 10 to the power minus 19 joules are incident on a surface of a clean metal plate of work function 3.2 times 10 to the power minus 19 joules. What is the maximum speed of the emitted electrons? So this is a question based on Einstein's equation. If we remember the Einstein's equation, the energy of a photon is equal to the work function plus the maximum kinetic energy. In this case, in order to find the speed, first of all we need to find the kinetic energy, so we can just rearrange for the K max, and K max is going to be equal to the energy of the photon minus the work function. So the energy of the photon is 4.8 times 10 to the power of minus 19 joules minus 3.2 times 10 to the power of minus 19 joules, and if we take those away, we're going to get 1.6 times 10 to the power of minus 19 joules of kinetic energy. So this is our maximum kinetic energy. Now remember, Kmax is just kinetic energy, so that's equal to a half mv squared. So what we can do is just rearrange for the velocity. So we can say that the speed is actually the square root of, if I move the 2 up there on the other side, that's going to turn into twice your maximum kinetic energy divided by the electron mass. So just looking up some numbers and plugging in, twice the kinetic energy in this case is 1.6 times 10 to the power of minus 19 joules. Our mass, the mass of the electron that's given in your formula booklet, which is 9.11 times 10 to the power of minus 31. And if we plug those numbers into a scientific calculator, we're going to get 592673 meters per second, which approximately up to 2 significant figures is 5.9 times 10 to the 6, or times 10 to the 5, sorry, multiplied by 10 to the 5 meters per second. So that leads us to A being the correct answer. Right guys, question number 17. Two guitars of equal length with different thickness are under the same tension and the strings are made of the same material. One of them has a diameter of 0.2 and another one has a diameter of 0.8. What is the value of the ratio elastic potential energy of the thinner over the elastic potential energy of the thicker string? Okay, well, the first thing to do when we encounter a ratio is just to write it out completely. So what is the formula for the elastic potential energy in the thinner string? So the formula of elastic potential energy is a half times the force times the extension. And let's say in the thinner string, we're going to call that, let's say that has an extension x1, and we're going to divide that by the, what happened here? Let's try that. We're going to divide that by the elastic potential energy in the thicker string. Let's call that x2 for its extension. So that's going to be divided by a half f times x2. Well, notice that almost everything is going to cancel in this ratio. This is normally what happens in ratio, that a considerable amount actually cancels out. So we can get rid of these half f's, and what we're left with is just x1 over x2. So in other words, if we find the extension in the thinner string and we divide that by the potential energy, if we divide that by the extension in the thicker string, we're going to get our answer. So let's get to it. The first thing we're going to notice is that they are made of the same material. They're made of the same material. That means that they have the same Young's modulus. Once again, let's say, I'm just going to say that wire 1 is the thinner one. So any index that you encounter of being index 1, that's the thinner one, and wire 2 will be the thicker one, like so. Well, we know that the two Young's moduluses are the same, so Young's modulus 1 is equal to Young's modulus number 2. Young's modulus in general is stress over strain, so we can say that the stress in the first string is going to equal to the stress in the second one divided by the retrospective strains, like so. Okay, well, let's start applying some formulas. We know that stress is force over cross-sectional area. So let's say that A1 divided by the strain, which is extension, x1, over the original length. Let's call that L. So this is going to have to equal exactly the same expression for the second string. So there's going to be f over a2 divided by x2 over the length. Now notice that the question says that the two wires are of the same length and under the same tension. So that means that we can cancel some things out. We can cancel the force and we can cancel the length. Okay, well, mathematically we can just rewrite the following expression as 1 over a1 over x1 is equal to 1 over a2 divided by x2. Additionally, if I just play around with the algebra, I can rewrite exactly the same expression just by bringing this a1 sort of downstairs in the fraction and this a2 downstairs in the fraction as well. So this becomes 1 over a1 x1 is equal to 1 over a2 x2. Now because I'm looking for the ratio of x1 over x2, I can just rearrange for that really. I can bring this guy over here, no problem. So what I'm be left with is 1 over a1 is equal to x1 over x2, and I get a factor of a2 over there, let's not forget that. And finally, I'm just going to bring my a2 on the other side, and what I get is that x1 over x2 is actually equal to a2 over a1. Perfect. So I've almost found my ratio over here. So x1 over x2 is a2 over a1. X1 over x2 is equal to a2 over a1. So let's find that ratio. This is equal to pi times the diameter over 2 squared, like so. And let's add some indices, and d1 over 2, all of it squared. So in this ratio, the pi's are going to cancel like so, and these two squares are going to cancel. This is going to equal to d2 squared over d1 squared. Remember this index 2, this was for the thicker wire, so that had a diameter of 0.80 squared divided by 0.20 squared. If we were to put those into a scientific calculator, let's do that. We're going to get 16 for the ratio, which is our correct answer. So this was actually quite an enormous amount of work for 1 mark, but we've reached the answer over here, which is 16. Let's make sure that we actually write the letter. So this is D. Okay folks, hopefully this makes sense. If you managed to find a much easier way, please let me know, and I'm going to make another video about it, or I'll just add it onto this video. Let's move on to the next question. Question 18, we're almost there guys. A ball is thrown at an angle of 30 degrees to the horizontal. The initial kinetic energy of the ball is K. No air resistance, hooray. What is the kinetic energy of the ball at maximum height? Okay, now the first thing to notice is that at maximum height, this ball is only going to have horizontal velocity. So the velocity vector is purely horizontal. So maximum height means only horizontal velocity. Only horizontal velocity. Okay, well, it says over here that the initial kinetic energy of the ball is K. So we can say that K is equal to half mv squared. Let's say that the initial speed of the ball is let's call it v. At maximum height, there's only going to be horizontal velocity. Now, what is the horizontal component of v? Well, if we imagine v to be acting like this at the very beginning, the horizontal component, that does not change, and if this angle here is 30, the horizontal component is going to be V cosine of 30 degrees. So at maximum height, the kinetic energy of this ball, let's call it Ke just to differentiate that. So Ke is going to be a half times the mass times, rather than V squared, I'm going to write V cosine 30, all of it squared. And now what I'm going to do is just expand all those brackets. So it's going to be a half times the mass times V squared cosine 30 squared, like so. Well, notice that actually this a half mv squared, that's actually K, isn't it? So this over here is exactly the same as this expression over here. So rather than a half mv squared, I can just write K. So this is equal to K cosine 30 squared. So I'm going to put cosine 30 squared into my scientific calculator. So let's do that, because 30 square it, that's 3 over 4, which is 0.75. So the kinetic energy at maximum height is 0.75 of the initial kinetic energy. Of course, that assumes that there's no air resistance. If there was air resistance, this horizontal vector will probably be decreasing a little bit as time goes on. But in this case, in the perfect world with negligible air resistance, then the horizontal component remains absolutely the same. So the correct answer is C. Second to last question, question 19. We have two resistors R and 2R. What is the ratio of the power dissipated in the first one over the second one? As always, the golden rule with ratios is to write down a formula for whatever is on the top of the fraction and whatever is at the bottom of the fraction. Now, what formula are we going to use for power? Well, we know that power is equal to IV. Because the voltage is constant in both of these branches, let's express I as V over R, voltage over the resistance from Ohm's law, multiplied by the voltage again, and power is just V squared over R. Okay, well, let's write down this fraction. So our ratio is going to be the following. So power dissipated in the R resistor, that's just going to be V squared over R, like so. And the power dissipated in the other branch is going to be V squared divided by 2R. Okay, the next thing we can do is we can do some cancellations, quite a lot of them really. So we notice that V squared is going to cancel. In fact, R is also going to cancel. So what we're left with is just 1 on top divided by 1 over 2. So 1 over a half. So this is going to equal to 2. So the correct answer in this case is D, 2. On to question 20, the very last question of today. So I've got the speed of light in air is 3.0 times 10 to the 8th, and the speed of light in a glass is 2.0 times 10 to the power of 8. From that we can work out the refractive index. We can do that in a minute. A ray of monochromatic light strikes the glass air boundary and at an angle of 80 degrees to the boundary. Can immediately see that there's a little trick over here. The angle of incidence is actually 10 degrees. So remember, our angle of incidence is always this angle here, which is to the normal, not to the boundary. So even before I read the rest of the question, I'm just going to put that on there. What is the angle made to the normal by the ray leaving the boundary? In other words, this is asking for the angle of refraction. The first thing we need to do is work out the refractive index of glass. let's call that just n1, the refractive index of the first boundary. Remember, the refractive index is just the speed of light divided by the speed of light in a vacuum divided by the speed of light in that particular substance. So this is equal to 3.0 times 10 to the 8 over 2.0 times 10 to the 8, which is essentially just equal to 3 over 2. So it's a fraction. Okay, well, now that we have the refractive index, we can then use Snell's law. Now, in your formula booklet, Snell's law is given as n sine theta is equal to a constant. Probably the best way to always rewrite this as n1 sine theta 1 is equal to n2 sine theta 2. Now remember, n1, we already know what that is. That's just 3 over 2. So 3 over 2. And we know what theta 1 is. This is our angle of incidence, is just 10 degrees. So sine of 10. That's going to equal to n2 sine theta 2. Now the refractive index of air is just 1. So we can assume that to be 1.0, and multiplied by the angle that we're looking for, sine theta 2. Okay, so what I'm going to do is just rearrange for sine theta 2. So sine theta 2 is just going to equal to 3 over 2 sine of 10 degrees. And obviously divided by 1, but I'm not going to write that because anything divided by 1 is exactly the same expression. So theta 2 is going to be the inverse sine of 3 over 2 sine of 10 degrees. And if we put that into our scientific calculator, what we're going to get is about 15.01, which up to the significant figures in the questions is just 15 degrees. So this is B, correct answer. Okay folks, so hopefully you have enjoyed this video and you found this useful. If there are any questions on the questions, please leave a comment down below and consider subscribing. Thank you very much.